In the 1880s, across the industrial regions of the United States, the refineries burned day and night. There were no warning systems, no unified safety standards, no reliable way to measure the dangers building in the air. Just fire, iron, and men moving through it as part of their daily routine. From the outside, these places represented progress. Tall smokestacks marked the horizon, pipes stretched in every direction. A steady glow of flame signaled production that never stopped. But inside those refinery yards, the reality was different. The danger did not announce itself. It settled quietly into the air, into the ground, into the machinery itself. And when it revealed itself, it did so without hesitation. Rockefeller's refineries were not designed as single systems, they evolved. Each expansion added new structures, stills, tanks, pump houses, often placed wherever space allowed. Over time, the result was a dense industrial landscape that functioned as one continuous machine. At the center of the operation were the still houses. These were large iron vessels, sometimes several stories tall, where crude oil was heated and separated. Beneath them, furnaces burned constantly, fueled by wood, coal, or byproducts of the refining process itself. Surrounding the stills were networks of pipes. Some ran along the ground, others stretched overhead on wooden supports. They carried crude oil, partially refined products, and volatile vapors from one stage of the process to another. Storage tanks dominated the outer sections of the yard. Many were large cylindrical structures, some built from riveted iron plates, others made from wooden staves bound together with metal hoops. They held thousands of gallons of oil at various stages of refinement. Walkways, often narrow and uneven, connected these areas. Workers moved constantly between them, stepping over pipes, navigating slick surfaces, and passing within arm's reach of machinery that operated under heat and pressure. Nothing in the refinery stood alone. Every component depended on another, and every part carried the potential to fail. The late 19th century was defined by rapid industrial expansion. Cities grew, factories multiplied, transportation networks extended across vast distances. This growth required energy. Before petroleum, lighting depended on candles, whale oil, or gas systems that were expensive and inconsistent. Machinery relied on lubricants that were often inefficient or unreliable. Petroleum changed that. Kerosene provided cleaner, brighter light. Lubricating oils improved the efficiency of industrial machines. New fuel products began to emerge, laying the groundwork for future technologies. Demand rose quickly, and with that demand came competition. Rockefeller's operations focused on scale and efficiency. Refining oil faster and more consistently meant controlling a larger share of the market. To achieve this, refineries expanded aggressively. Production targets increased. Equipment was reused, modified, or improvised. Facilities grew faster than engineering standards could keep up. At the time, there was limited understanding of petroleum's full behavior. The industry knew oil was flammable, but the behavior of vapors, pressure systems, and chemical interactions was not fully understood. In many cases, knowledge came only after failure. The refining process relied on controlled heating. Crude oil contains multiple components, each with its own boiling point. When heated inside a still, lighter elements vaporize first, Heavier elements remain behind. These vapors travel through pipes where they cool and condense into usable products. This process required balance. Temperature had to remain steady. Pressure had to stay within safe limits. Flow between systems had to remain uninterrupted. In modern systems, this balance is controlled automatically. In the 1880s, it was controlled by observation. Workers judged conditions using indirect signs: the intensity of a flame beneath a still, the sound of liquid boiling inside metal walls, the vibration of pipes under pressure. If a flame burned too strongly, temperature could rise too quickly. If a valve failed, pressure could build in one section of the system. If flow slowed, vapors could accumulate where they were not expected. There were gauges, but they were not always accurate. There were valves, but they did not always seal properly. There were procedures, but they depended on individual judgment rather than consistent standards. The system worked most of the time, but it left little margin for error. The most significant risk inside these refineries was not visible. It was chemical. Crude oil and its refined products release vapors continuously. These vapors are lighter than liquid, but heavier than air in certain conditions. They move unpredictably, settling in low areas, drifting along surfaces, or collecting in enclosed spaces. Workers could not see them. Sometimes they could smell them, but smell was not a reliable indicator. Certain vapors carried a strong odor. Others were nearly undetectable. A worker might enter an area that appeared safe, unaware that the air itself had changed. These vapors were highly flammable. In the right concentration, they could ignite instantly. The source of ignition did not need to be large. A small flame from a lantern, a spark from metal contact, even heat from an exposed surface. What made the situation more dangerous was familiarity. Workers operated in these conditions every day. They walked past open flames. They worked around leaking oil. They navigated spaces where vapors formed regularly. Over time, these conditions became normal. And when something becomes normal, it becomes easier to underestimate. Failures inside the refinery rarely began with a single dramatic event. They developed gradually. A valve might begin to loosen due to vibration. A pipe joint might develop a small leak. A storage tank might expand under heat, placing stress on its seams. Individually, these issues appeared manageable. Workers often addressed them with immediate fixes: tightening a fitting, wiping away excess oil, adjusting the heat beneath a still. But these solutions did not remove the underlying risk. They delayed it. As production continued, small issues combined. A leak allowed vapors to escape. Heat increased the rate of evaporation. Airflow conditions trapped those vapors in one area. At some point, conditions aligned and ignition occurred. Sometimes it was a flash fire, a brief but intense burst of flame that moved rapidly across a surface. Other times, it was more sustained. If fuel sources were abundant, the fire continued to spread. Pipes carried flammable material. Tanks held large volumes of liquid. Wooden structures provided additional fuel. What began as a small ignition point could expand within seconds. The critical issue was not that individual components failed. It was that the system allowed failure to spread. The refinery was interconnected. Pipes linked tanks to stills. Stills depended on continuous fuel supply. Storage areas were positioned close to operational equipment. There were few barriers. If a fire reached a pipe, it could follow the fuel inside it. If a tank was exposed to heat, its contents expanded, increasing internal pressure. If pressure exceeded structural limits, the tank could fail. Each failure introduced new sources of fuel. Each new source intensified the situation. This created a chain reaction, not because of a single mistake, but because the system was not designed to contain problems once they began. The refinery operated efficiently under normal conditions, but under stress, that same efficiency became a liability. The workers inside these refineries were not unaware of risk. They recognized patterns. They understood which conditions felt unusual. They paid attention to changes in sound, temperature, and smell. Experience mattered. New workers often relied on guidance from those who had spent years in the environment. There was an informal system of knowledge: which tanks to avoid during hot weather, which valves required closer attention, which areas accumulated vapors more frequently. But this knowledge had limits. It was based on observation, not measurement. Workers did not have access to precise data. They made decisions based on what they could perceive, and perception could be misleading. Fatigue also played a role. Long shifts reduced attention. Repetition made tasks feel routine. Routine reduced caution. A worker performing a familiar task might not notice subtle changes. And in an environment where conditions could shift quickly, those changes mattered. Despite this, workers continued. The wages provided stability. Employment opportunities were limited in many areas. The refinery offered consistent income. It also created a sense of shared experience. Workers depended on each other. They communicated informally. They watched for signs of trouble. They supported each other during demanding tasks. But no amount of experience or cooperation could eliminate the risks built into the system. Over time, the refining industry began to evolve, not through a single reform, but through gradual change. Repeated incidents highlighted weaknesses. Engineers began to improve equipment design. Storage tanks were reinforced. Pressure relief systems became more reliable. Materials improved in quality and consistency. Understanding of petroleum chemistry expanded. The behavior of vapors became better understood. Ventilation methods improved. Separation between critical systems increased. Firefighting techniques also advanced. Specialized equipment was developed for handling oil fires. Better training improved response times and effectiveness. Regulations began to emerge. Standards for construction, operation, and safety were introduced. These changes did not eliminate risk, but they reduced it. Modern refineries still operate using the same fundamental principles: heat, pressure, volatile materials. The difference is control. Today, these factors are monitored continuously. In the 1880s, they were managed through experience and judgment. Rockefeller's refineries helped build an industrial world that depended on energy. They transformed crude oil into something useful, something essential. But the process that made that transformation possible carried risks that few fully understood at the time. Inside those yards, the danger was rarely obvious. It did not always appear as fire or failure. It existed in the air, in the pressure within metal, in the quiet interaction between heat and vapor. The men who worked there adapted to it. They learned to move through it. They trusted their experience to guide them, and for many, that was enough, until it wasn't. Because the true nature of those refineries was not defined by what could be seen. It was defined by what remained unnoticed, until the moment it could no longer be controlled.